Hey everybody, it's Dr. J, and today, yes, today, we are talking about kinetics. So let's talk about some chemistry. All right, so today we're going to actually look at an example of experimental data. Okay, so one thing about kinetics is that in order, right, to get any type of number-wise with kinetics or get anything with data, you must do experiments. Okay, so that's the first thing. Basically, you're doing experiments to determine the kinetics. So that's the first. Okay, so today we're going to find the kinetic rate of expression, and then we're also going to find the overall order of reaction. Okay, and we got our reaction here. So we got mercury 2 chloride with this oxalate ion forming mercury 1 chloride and some carbon dioxide and chlorine over there. Okay, so basically, for instance, we did 3 experiments, right? And then in each experiment, we basically change how much reactant we're going to use here, okay? So in experiment 1, we use zero point 0.1 molar of this mercury chloride. Experiment 1 with the oxalate, we use 0.1 molar, 0.15 molar. And then we have our initial rate here at 2 times 10 to the negative 5. And then we did it again with experiment 2. So we basically kept our mercury chloride the same, but then we doubled the amount of our oxalate. And we can see what happens to our rate right here as it went from 2 times 10 to the negative 5 to 8 times 10 to the negative 5. And then experiment 3, in this case, we cut, right, our mercury chloride here and leaving this oxalate the same. And then we can see what happens with the initial rate here. So let's talk about how we're going to find the kinetic rate expression and the overall order of our reaction today. So first thing you always want to do with these kinetic problems is you need to set up your rate law, right? So if you remember, right, rate equals the K times the concentration to whatever order, right? That's what we're looking at here. So because we have 2 reactants, our orders are going to be respected, right? It's going to be towards those reactants. Okay, so basically each reactant is going to have its own order. Okay, so rate equals K times our concentration of mercury chloride, right? And then we don't know the order, so that's what we're doing here. So I'm just going to put a variable here, X, and then we have our C2O4, our oxalated ion here. All right, and once again, I don't know the order, so I'm just going to put Y here. So this is what we're solving for. We're solving for X and Y in this case, all right? We're solving for those two. Now, here's the first step that we're going to do here. Step 1 is we're going to find 2 experiments where the concentration of one of the reactants stays the same and the other is changing. So we need to just look at 2 experiments to see which one is changing. All right, so we have our data here and we're looking for 2 of the 3 experiments. Okay, in this case, we're looking for one of our reactants to have a concentration that's changing and then the other reactant to stay the same. So you can use really any of the experiments. All right, it just depends which one you want to use. So in this case, if I look at what I have here, I'm going to look at 1 and 2. All right. And in this case, my mercury chloride is staying the same at 0.1 molar for both experiment 1 and 2. But if I look at my oxalate ion, I'm going to see that, well, the concentration is changing, right? It went from 0.15 to 0.3, all right, molar. So this is good, right? So I could use this, right, because this has this changing value here, okay? So, right, I picked my 2 experiments, and now I'm just going to plug in my data into this handy-dandy formula here. All right, handy-dandy. So we're going to have, basically, this is set up to where our rate of our experiment 2, right, over our rate of experiment 1 equals to our concentration of experiment 2 over the concentration of experiment 1. Okay, and this is the same thing here, right? We understand with the exponents, they're basically raised to the same power, so it's just rewritten here, but it's the same thing. All right, so let's actually look at our data and let's plug this into our formula here. And what you guys want to know is that we're going to do this every single time whenever we're trying to find these orders, right? It's literally the same thing. Rate of our experiment over rate of another experiment equals to our concentration of our same experiment over the concentration of the other experiment. So if I look at my data, I'm going to use my rate of experiment 2, which in this case is 8 times 10 to the negative 5. I'm going to place that here. And then the rate of my experiment 1, which is 2 times 10 to the negative 5, which I found from experiment 1 here. So literally it's rate of experiment 2 over experiment 1. Bam. That's what we got here. Now we're going to set that equal to our concentrations. So I got concentration of my changing reactant. That's the key thing, everybody. You want to use the one that's changing. You don't want to use the one that's staying the same, right? You want to use the one that's changing. So in this case, it's our oxalate ion here, right? So we got our concentration of 0.3 molar over our 0.15 concentration from experiment 1. So experiment 2 over 1. Okay. And then since we're still solving for our order, that's just y right there. That's what we're solving for. So if I do my math here, right, 8 times 10 to the negative 5 divided by 2 times 10 to the negative 5, I'm going to get 4. And then 0.3 divided by 0.1 gives me 2. All right. And if we can look at here, right, we can look at it and then we can see, right, well, if 2 raised to y equals 4, the only thing that's going to get me to equal 4 is that this y must be 2. All right. So that means that my order is second order. All right. We have second order for this particular concentration. Now, if you're ever in a state to where it's like, okay, you can't necessarily tell, right, that this y is going to equal 2, you can always do some math too. So basically, y'all, if y'all remember this, right, there's log. I'm going to take the log of 4, right? So log 4, I'm going to log both sides. So now I got log 4 equals to, now what I did here is basically it was log 2y, but if you remember, right, from, what is this, algebra? Yeah, algebra, is that you can bring that exponent down in front of the log to where now it looks like this, y equals log 2. Then you could just rearrange and solve for your y. So you're going to divide log 2, and now you got log 4 divided by log 2. If you do the log of both of these, you're going to get 0.602 divided by 0.301, which is going to give me the same answer at 2. Okay. So, like I mentioned, I like to show you guys multiple ways to do this stuff. So there's 2 ways to get the same answer here, right? You can either look at it, or you could just take the logs, right? If it's something that may be a little bit more complicated. All right. So we just determined, right, that our second order, right, this right here is C2O4 is second order. Now, right, so now we have this as our rate law so far. We have rate equals K HgCl2 raised to X. So we still don't know that order. But now we do know, right, this reactant is second order. So what are we going to do here? Right? What are we about to do here? So let's find the order for this reactant here. So basically what we're about to do again is the same process. I'm about to look at my experiments and see, well, in this case, which of these experiments is changing, right? Does my concentration change? 2 and 3, right? And notice, right, it goes from 0.1 to 0.05. So that's changing, and then you always got to double check. Is the other reactant staying the same? In this case, it is. It's staying the same at 0.3. All right, so it's staying the same. So I know which experiments I'm going to use, 2 and 3. Now, let's just plug in my data, which is from these 2 points here, into my handy dandy little notebook. Y'all remember Blue's Clues? Shout out to Blue's Clues. All right. So anywho, we got our rate of experiment 2 over rate of experiment 3. Concentration of experiment 2 over concentration of experiment 3. And then once again, this is raised to our x because this is what we're solving for. So I'm literally going to take what I have here in my data. The rate I found to be 8 times 10 to the negative 5. bam. And then I got the rate of experiment 3, which is 4 times 10 to the negative 5, bam. All right, so we got that set away. And then we're going to look at the concentration here. All right, so that's going to be 0.1 divided by 0.05. Okay, and then once again, that's raised to x. So we're going to do some division here, right? And this is going to give me 2. And then 0.1 divided by 0.05 will give me 2 as well. And, you know, based on just looking at it, right, I want to know that, well, if I got 2x and it has to be equal to 2, the only thing that's going to give me the 2 is my x has to be 1. Right? 2 raised to 1, it's going to be 1 here. Okay. So my x is 1. My x is 1. And since we know that our x is 1, now we can plug it into our final rate law. So our rate equals K HgCl2, right, our mercury chloride, raised to 1. So notice, right, how I don't have 1 here. It's kind of implied. If you don't have a number there, it just means that it's 1. Okay, so it's 1 here, right, which we found here. And then, right, we still got the same second order for our C2O4 here. So this is my final kinetic rate expression here. Now, if I want to find the overall order of the reaction, I'm just going to add both my orders together. 1 plus 2 gives me 3. I can do math, y'all. I can do math. Okay? So that's it when it comes to solving, right, for your rates of your kinetic rate of expression and your overall order reaction. Okay, now a couple of things I do want to point out. You know, this is what we got here. And some people might think in their head that, well, I can just, you know, look at the equation and be like, well, if there's 2 there, it's going to be second order, or if it's 1 there, it's going to be first order. You don't want to do that, okay? So the coefficients are not going to help you with the orders. So you always want to go about the way we just did, okay? So that's just good to know. The orders are not going to correspond with the coefficients, all right? So you always have to do your math and all that type of stuff we just did to find those out. Now, what if, right? What if we had to calculate the rate constant? A shocker, right? No, it's not a shocker. We're all good here. We're all good. All right, so if we need to find a rate constant, this is what we're going to do, everybody. All right, so we're just going to plug in our data, right, that we have here from any of the experiments. It could be from experiment 1, 2, 3. Okay. So we plug in that data, then we just have to do algebra and solve for our K, right? Because if you remember, K is the rate constant. So let's do this example, right? Let's do this. So I'm going to use experiment 1, this data here, tell me solve for my K. So what I have here is my rate equals K, HgCl2 raised to 1, C2O4 raised to 2. So this is our kinetic rate expression we just found out. Now, I'm just going to solve for K, right? Because that's the only thing I don't really know. So if I solve for K, I'm going to have to divide my concentrations on the other side. And then it's going to look like this. So K equals rate over concentration. Concentration raised to 2. Okay. And then since I'm using my data from experiment 1, literally all I have to do is plug in. So my rate for experiment 1 is 2 times 10 to the negative 5. My concentration is 0.1. And then the concentration is 0.15, but remember it's raised to 2. Okay. We do our math. We're going to multiply. We get our 2 times 10 to the negative 5 still. And then we get 2.25 times 10 to the negative 3. All right. And then notice the units is m cubed now. Now, right, we just have to divide. All right. We divide 2 times 10 to the negative 5 divided by 2.25 times 10 to the negative 3. And then for my K, my rate constant, I'm going to get 8.88 times 10 to the negative 3. All right. And my units are here. M, negative 2, and seconds, negative 1. All right. That's my final units here. Okay. And that's it. That's literally it, everybody. We're just plugging in our data. to solve for our K. And like I mentioned before, you can use any one of these experiments, 1, 2, or 3. We're going to get the same value for our K here.